Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And very good morning. Today we'll begin the chapter 3, which is the network layer. I think this is the core of the data delivery across the internet. For example, you can think of the data network is like the post office of the internet. So it will decide how your data is packaged or is packet and routed from sender to a receiver. Okay. So by the end of this chapter, you should be able to explain how the network layer provides the connectivity, how they manage the addressing and also to perform the routing. Okay, you'll also will understand how the IPv4 the structure of IPv4, how to do subnetting. Okay, and also the packet structure. Okay, right. So let's start with uh, the introduction of network. Okay, so let's take a look at how the communication occurs across the network layer. And we use the example of this figure. For example, you have Ahmad and Bob, that two users who wants to communicate across the different network. Okay, we have Alice and Bob here. Okay, so we start from Alice at the top left. Okay, where she initiate to communication. She initiate to start the communication. Okay, like browsing the web or sending a file. Okay, and her data will go across the application layer, starts at application layer. Okay, and move down to the transport network, data link, and finally to the physical layer. Okay, and then this is to show how in the stack protocol, bagaimana dalam protokol ni berlaku dalam dia punya laptop lah. Okay, and now the Alice punya data, okay, was traveled through several devices. Okay, for example, the first point is the router. We have R1 here, and then to the R2. Okay, and we can see here how this router handles up to the network layer. Okay, and we can see that here the routers don't need to interpret data, okay, in this layer. Next, the data continues through the national ISP. Okay, this is like the infrastructure that you have that represented by R3, router 4, and router 5. And we have the one WAN switch here. Okay, where this is the part of the network that enable the long distance routing between different regions or different networks. Okay, remember we have one MAN, LAN. Okay, so this is the one. Okay, and from here, okay, the data will move to another ISP. Okay, through the router 6 and router 7, and finally we'll reach Bob, okay, which is our recipient at the bottom right. Okay, like Alice, Bob also will have the system that resembles the data moving it upward from this physical to the application layer. Okay. And we also can see this dotted line is point to point one links, okay, which connected the routers. And we have LAN switch here. The LAN switch is used in the local network. And as for the WAN switch, used as the backbone or the core switches of this network. Okay. So I think what you need to understand from this figure is the network layers will enable end-to-end communication between Alice and Bob. Okay, and even though they are in entirely different network, the routers will work together to deliver packets across various paths and providers. Okay. And we also can say that we have the flexibility and scalability, okay, in handling diverse routes and technologies. Okay. Right. So next is we know that at this network layer, they provide the service that allow the data to travel across the interconnected networks, or we call it as the inter network. Okay. And these routers is like a bridge connecting a smaller island, okay, like connected the LAN and WANs. Okay. So the key services that provide in the previous network ataupun previous figure, for example, at the source of Alice, okay, the data is passed from the transport layer, okay, into the IP datagram and then sent to the data link layer. And at the destination where Bob is a host, will process by reverse process, and we call it as the decapsulate. Okay, this is encapsulate ataupun dia bungkus sebelum dia hantar data tu, and then at the Bob punya side, it will decapsulate, dia akan buka ataupun nyah bungkus kalau dalam bahasa Melayu, uh, and yeah, we call it as decapsulated. Okay, this is the reverse process. And the routers is used only the routers in between, okay, in between only the network, okay, data layer, data link, and the physical layer. Okay, tiga saja kita guna. So while Alice and Bob use all the 5 layers, for the routers will only work efficiently with only 3. Okay, the network, data link, and the what we call another one, a physical layer. Okay. Okay. The next is the most important duties in network layer is packetizing. Okay. So what is the packetizing? For example, at the sender, it takes the transport layer segment and will add the header. Okay, the header we call it as the that contain the destination IP address and pass it down. Okay, and at the destination host or at the receiver, the data is decapsulates. Okay, and payload is handed back to the transport layer. Okay, if the data or if the packet is too large, okay, it will be fragmented along the path and reassemble at the destination. Maksudnya dia kecil-kecilkan dulu and then dia gabungkan balik at the destination. Okay, and here the routers are not allowed to decapsulate or to modify the source or the destination areas or destination address. So they only can fragment if necessary. Okay, that's why the packet integrity, I think, it's important. Okay. And in the network layer, it's also handle the routing, where routing is about to find the best path to for data to travel. Okay, so there can be have many routers, and the router must decide which one is optimal using the routing protocol. Okay, this protocol, okay, will generate the routing tables, which help the routers know where to send the packet even before the communication begin. Okay, so I think what you need to know about the routing is about to prepare the road before the vehicle or the data starts the journey. Okay, and we have the forwarding here. Okay, forwarding is a real-time action performed by a router. Okay, when a packet arrive, okay, the router will check the destination address and will forward to the forwarding table. Okay, the table will tell you ataupun will tell the routers which output interface to use to send the packet to the next port. Okay, so for example, you can see here the packet will enters at the port 1, which is label number 1 here. Okay, so the router will check the forwarding table. Okay, and then it find the entry. For example, it said if the label is L1 on port 1, okay, forward to the label number 2, which is L2 lah. Okay, and then the router swaps the label from L1 to L2, and then the packet now leaves the port 2, okay, with label 2, L2. Okay, and this is about the error control. Okay, the network layer does not provide the full error control because the datagrams, we know that it may be fragmented, and checking each fragment would be inefficient. Instead, the header, okay, includes the checksum for basic error detection. So if an error detected, the network layer will use the internet control message protocol to report problem like unreachable destination or any route issues. Okay, so ICMP is Internet Control Message Protocol. Bila belakang pasal adik tak siap belok pasal bola. Okay. So unlike the transport layer, the network layer does not handle the flow control. Okay, and the network layer does not directly provide any flow control. The packets or the datagrams that send as soon as they are ready, uh, regardless or without any attention to the readiness of the receiver. Maksudnya dia tak apa tak kira receiver tu ready or not, the sender will just send a data because why? Because the network layer assume that upper layer will handle the buffering and timing. So this will makes the network layer simpler and avoid any unnecessary complexities. Okay. And when too many packets are sent into the network, we will face the congestion. Okay. The routers may drop packets or making the situation worse. And we know that the transport layer may try to recover the lost packet, leading to the even more congestion. So in this continuous, the network can crash and no data will be delivered. Okay. Hence, I think we need to control the congestion before the network layer. The congestion control is usually handled above the network layer to keep things efficient. Okay. And lastly, I think we need to know about the QoS, the quality of service. For example, when we use the application like video calls or live stream that need a fast and reliable services. This is where the QoS comes in. Okay, the QoS is to ensure high priority data that will get delivered on time. Okay, but most QoS control normally done at the upper layer, not in the network layer. Program networks, every packet is independent. Okay. Each packet may have a different path. Okay. And they can arrive out of order. Okay. There is no relationship between packets belonging to the same message. The routers is handle each packet separately. Okay, and there is no memories on previous one. So as you can see here in the sender side, the sender is preparing to send the message, and the message is divided into 4 packets. Okay, and the packet will be sent individually, okay, into the network from R1, router 1, and then inside the network, okay, this is the connectionless network, meaning that the packet is treated independently. Okay, the routers do not keep track of any state or previous packet. Okay, the packet also may take different routes to the destination. Okay, for example, we have the packet 1 who go through R1, R4, R4, and then R5. Okay, and for the packet number 2, it goes through R1, R2, and R5. Packet 3, R1, R3. Okay, and R4 and R5. Okay, so each path is chosen based on the current routing decision. For example, it may consider the speed, congestion, and etc. Okay, and at the receiver side, okay, all packet will arrive at router number 5 and then will reach the final receiver, and they uh, arrive also out of order. For example, it received 1342 instead of the sending sequence is 4321. Okay, so this is the connectionless. Okay, the router only looks at the destination address to forward the packet. Okay, this is destination address B to be forward to the interface 2, for example. Okay, the source address is only used for error replies if needed. Okay, for example, and each packet will be sent one by one lah. Okay, at the incoming packet, the packet arrive at the router via interface A. So where the packet contains SA, which is the source address, DA, the destination address, and also data. So in this example, the destination address is B lah. Okay, B. Okay, so how to explain this figure? So for example, the router received the packet at one of the interface. For example, here we have one. Okay, it looks up the destination address B. Okay, so in this forwarding table, okay, in this forwarding table, the destination B should be forward to the interface number 2. So the router forward the packet through interface 2 without modify any source or the destination address. Okay. So this is the virtual circuit approach for the example of the connection oriented. Okay, in this virtual circuit network, we first set up a path for all packets in session. So after that, all packet follows the same route in sequence, just like a phone call. Okay, 4321, and this setup at consistency but need extra setup time. Okay, so what happened here? Okay, at the sender host, okay, uh, the sender want to send the message to the receiver. Okay, and it's broken into packet 1, 2, 3, 4, and it follow the exact same path through the network. We have R1, R3, and R4 to the receiver. So this predefined path yang warna biru ni, it's called as the virtual circuit. Okay. So this virtual circuit is created between sender and receiver throughout R1, R3, and R4 router. And for the data transfer, the packet 1 to 4 travel in order along this circuit path. Okay, there's no rerouting, and all packet arrive sequentially at the receiver. Okay, unlike the previous one, which is the connectionless method, this method follows the same route, so there is no chance out of order delivery. So in virtual circuit network, we first set up the path for all packet in session. So after that, the datagram can all follow the same path, okay, in sequence. Okay, and for example, here we label as the MPLS, which is the label switch network or the connection oriented network. Okay, the router is now in the center, and it will receive the packet at port 1. Okay, the label is L1, and we will use this forwarding table sorry, to look up what to do with the packet label 1. Okay. So first we will find the packet with label L1 at the port number 1, and then it will be forward to port number 2. And now it's relabeled as L2. Okay, so now the packet will be out as a new label, which is L2 towards the router. Okay. So this is the example of label switching where the router use label, okay, not IPs to forward the packet. Okay, so you can see it as the train station that switch track using the train numbers instead of check every passenger's tickets. So we have the transmission delay to measure the performance. Okay. To measure the performance, we look at the delays. The delay means how long it takes for a packet to travel. So there are two types that we will discuss next. The first one is the transmission delay, where it is the time to push all bits of packets onto the link. Okay, for example, we have a bigger packet or a slower link will have or will took a longer delay. So this is the formula for transmission delay. So delay is equal to packet size or packet length divided by the transmission rate. Okay. And for the propagation delay, it is the time it takes for a bit to travel from point A to point B in the transmission media or across a medium. So for the propagation delay, it will depends on the distance and speed. For example, if you use the copper wire or if you use the fiber, the speed of sending the data will be difference lah. Okay, so this is the formula. Propagation delay is equal to distance over the propagation speed. So now we have the processing delay and also the queuing delay. Uh, Right. So I think for this one, you can, so as for example, for the processing delay, we have what is the time the required time for a router or a destination host to receive packet from its input port, to remove the header, to perform an error detection procedure, and also to deliver packet to the output port. Okay, so the processing delay may a little bit difference from for each packet, but normally is calculated as an average. So this is processing delay is equal to time required to process a packet in a router or a destination host. So as for the queuing delay, it is the time packet waits in input and output queues in a router. And for the total delay, so assuming that the equal delay for senders, routers, and receivers, the total delay from source to destination delay is a packet encounters that can be calculated. So if we know the numbers of routers in the whole path. So for example, we have the n plus 1, okay, and this is the total delay of transmission, propagation, and processing delay plus n, and this is the queuing delay. All right. So for the true throughput. So let's see this example. So this is the example or the concept of throughput, which refers to the actual rate at which data is successfully transmit from one source to the delivery source. So for example, to the source to the destination. So let's take a look at this figure. Okay, we have a path from the source to destination where there are three links, link 1, link 2, and link 3, with two routers in between, R1 and R2. Okay, so for the link 1, it transmit at the transmission rate or at the speed of 200 kilobit per second. Okay, but when it reach the router 1, it can continue at 200 kilobit per second, because link 2 only support 100 kilobit per second. So the data must queue at the router and send out at 100 kilobit per second. So now we are at router 2, where the next link is 150 kilobit per second. But at previous link, we only have 100 kilobit per second worth of data uh, arriving. Okay, that means that the third link will be underutilized. So uh, even though some link can support higher speed, the overall data flow is limited uh, by the slowest link in the past. For example, here is link 2 lah. Okay, so this lead us to a conclusion that we can say that the average throughput of the entire path is determined by the minimum transmission rate among the links. So in this case is 100 kilobit per second. Okay. All right, so lastly, before we go to the 3.4, we have the packet loss. So we know that when the data is transmitted through the network, especially over the internet, some of the packet will be lost. Okay, so this is normally due to the network congestion or buffer overflow. Okay, so maybe you can imagine when a router is receiving multiple packet at the same time. Okay, so if the router is still processing a previous packet, the new one will wait in the input buffer, but the buffer has a limited space. Once it's full, any new incoming packet will be dropped. And now we have the problem when the packet is dropped, it often needs to be resent, which cause even more congestion and more packet loss, and it will reduce the overall network performance. Okay, so I think here we can say that that is why the important to manage the network traffic efficiently and to use the appropriate protocol that can handle retransmission efficiently. Okay, now we continue with IPv4 addresses. Okay, so as for the introduction, okay, we are now entering the address space. Especially, we would like to focus on IPv4 address space. Okay, so we know that each device on a network needs a unique address, and it's known as the IP address. Okay, this is used to communicate. Okay, and IPv4, okay, use 32-bit address, which means that it can support up to 2 to the power of 23. Sorry, 2 to to the power of 32. Okay, about 4.3 million unique addresses. Okay, this 32-bit address is important to identify the connection to the internet, not to the device itself. Okay, if a device move to a different network, its IP address will be changed too. Okay, so what you need to understand about the address space is IP address define the connection, not a static device. Okay, so there are three ways to represent IPv4 address. Okay, the first one is the binary notation. So binary is base 2. Okay, and it is a 32-bit sequence of 1 and 0. Okay, and the second one we have the dotted decimal notation. For example, if you see the format of four decimal numbers that's separated by dots. Okay, for example, we have 192.168.0.1. So that is the example of the dotted decimal. Okay, the next one we have the hexadecimal. Okay, so the hexadecimal is base 16. Okay, and then this means that the 32-bit address has eight a hexadecimal digit, and it's always used in network programming. So this is binary. This binary is equal to this dotted decimal, and if we transform to the hexadecimal, it will be 8-bit hexadecimal digit. Okay. Next, we have the address space that what we call it, the hierarchy in addressing. Okay, and we can say that it is divided into two parts. The first one is prefix. Okay, yang depan ialah prefix, and the second one is the suffix. Okay, the prefix is define the network, and the suffix is to identify the specific device or the specific host within that network. Okay, and the full 32-bit address is illustrated as a horizontal bar. And first is prefix, and the second part is suffix. Okay, remember, prefix to define network, and the suffix is to define the connection. Okay, so on the left side, which is the prefix, is helpful for routers to decide where to forward the packets, and for the right side, the suffix is to define the individual devices, such as if you have the printer, PC, or a server connected to the network. Okay, and we also can say that IP address can be can be divided into classes. Okay, so for example, here we have 5 classes, A until E. Okay, for the A, it's begin with 0, and it normally used for a very large network. Okay, and for the class B is the medium size network that start with 10. Class C is a small network, start with 110, and class D and E normally used for multiple and experimental purposes. Okay, the problem with this class system was the wastage. For example, many organizations got more IPs than they needed. So To address these cons, we now move to um, the classless address. Okay, so this is the example of the classful address. Okay, right. So the classless address, uh, or normally the CIDR, it's known as the CIDR, classless interdomain routing. Okay, so unlike the class address in the previous slide, um, so we know that in the previous system, the address was divided into blocks, okay, like class A, B, and C. And for the classless address, it let us divide the IP into the variable length block, okay, based on the demand or the actual needed IPs. Okay, so we can say that this is more efficient and flexible. For example, if you look at this diagram, okay, it shows several blocks. We have block 1, 2, block I, block M, and we can see here the block are not same size. Okay, so each one is a power of 2, which is a rule we must follow. Okay, the size of block must be in 2 to the power of n. Okay, for example, to the power of 2, to the power of 4, 8, and so on. Okay, and as in the previous class, we also divide this IP address into two parts. Okay, the prefix which define the network. Okay, and so this is a prefix, and the suffix is to define the device or the nodes. So this allow the ISPs to allocate IPs in just right block size for a customer that help to prevent the waste of addresses. Okay. And now we want to identify how many bits are used for the network part. Network part, for example, we use something called a slash notation. Okay, and normally we see this is the example of slash notation, and you always see the IPs written like 192.168.1.0 and slash 24. Okay, and that slash mean that the first 24 bits are for the network. Okay, and then for the rest are the remaining 8 bits are for the host. Okay, and so we have another example here. The IP address made of 4 bit. Okay, sorry, 4 byte. Okay, and if we say slash 8, meaning that the first byte is for network. Okay, and then and it's a big network lah kalau 8 ni. Okay, um okay, and then the remaining 24 bits are the host address. Okay, so why I say it is the slash 8 adalah big network, because we can have the what yeah get to the power of 24. To the power of 24 is equal to around 16 16 juta. Okay, 16,777,216 addresses. Okay, the total of 2 to the power of 24. Okay, so it's is like 16 million usable addresses. Okay, so imagine if you own this block, you can connect over 16 million devices. Okay, so this is how IPs were allocated in the early IPs. All right, and so if you have a very big block, meaning that very few organizations use these days. Okay, for the mid-size block, we have the example here, slash 12. So meaning that the 12 bits are fixed for the network, right? So that's 23 in binary is equal to 8 bits, and 14 in binary is equal to 8 bits, and we only takes the 4 bits, and that 12 bits network. So remember, we have the total of 32. Okay, 32 minus 12 is equal to 20. So that 20 bits left for the host. So 2 to the power of 20 is equal to around 1 million, right? And so that 1 million can be used for the addresses. Okay, so and then we have the third one is for the small subnet. Okay, so slash 25 means that 25 bits for the network part. Network part. Okay. So the remaining of 7 bit for the host. Remaining maksudnya 32 tolak 25 sama dengan 7. Okay. So 2 to the power of 7 is around 128 in total, and then we have we need to minus by 2, and then we will have 126 usable IPs. Okay, so this is perfect for VLAN, a small office or department. Okay, so that so this idea of having the slash notation, we are not wasting the IPs. Okay, we use the IPs a very efficient way. So in short, CIDR with slash notation help us to assign just the right amount of IPs based on the real need. So tiada pembaziran lah. Okay. And now let's move deeper into classless addressing. Okay, specifically on how to calculate the address block using the slash notation. Okay, so this is the format, like if you see slash 24 slash 27 etc. So for example, if you have the if you are given the IP address block like 192.12.64, and then we have this slash 27. Okay, so that slash 27 meaning that your prefix length. Okay, the first 27 bit of the IP address are fixed on the network part. Network part. Okay. So there are three important things that we need to know when we are working with address block. Okay, the first one is the number of addresses. So you need to use this formula, n is equal to 2 to the power of 32 minus n. So where 32 is the total number of bits normally used in IP v4, and the n is uh, the number of bit used for the network or for the prefix. So for example, tadi I cakap dia ada slash 27. So what we do is 2 to the power of 32 minus 27 is equal to 5. So 2 to the power of 5 is equal to 32 total of IPs. Okay. Next, you need to know what the first address in block. Okay. To find this, we keep the first n bits, which is the prefix, okay, and set the remaining bits 32 minus n to all zeros, okay. And so, for example, if you have 162, 168 dot 12 dot 64 slash 27, so the binary of the IP start like the last of the IP become like 0000. Okay, and then we have the last address. So you need to keep the first bit. This time set the remaining bits. Okay, 32 minus 0. 32 minus n. Okay, and so this will give you the broadcast address, right? So this last IP in the block, and we use to broadcasting all devices. Okay, so let's see the example of the concept of classless addressing. Okay, we are looking at the network address of 167.199.170.82 slash 27. Okay, now that slash followed by a number, in this case 27. Okay, and this slash 27, okay, can give us how many bits, tell us how many bits in the address that are dedicated to the network portion, or how many are for the host portion. Okay, so how do we break down these addresses and figure out the important information about this network? Well, the first thing is we can determine is the number of address available. What is the number of address available? Okay, so slash 27 tell us that 27 bits, okay, is used for the network ID. Okay, so since IPv4 has the total of 32, okay, so 32 minus 27, so you got 5. So 2 to the power of 5 is equal to 32. Okay, and this is the total network address. Okay, now that's a first and last address. Okay, the first address is the network address itself, and the last address, okay, is the broadcast address. So all these addresses is in between can be assigned to individual hosts on the network. Okay, so how to define ataupun how to get this first address? To get the network address, we need to ensure that all host bits are set to 0. Okay, and if we look at the binary representation of the given address here, okay, the last 5 bits, okay, this is last 5 bits are the what the host bit. Okay, so to find the first address, we set the last 5 bits to zeros, and that will give us these binary numbers, which is, if we translate to the IP address, we will get 167.199.170.64 slash 27. So that slash 27 will be remain the same, as it still define the network portion. Okay, so for the last address, okay, or also we call it as the broadcast address. Okay, same as previously, we keep this 27, but only set host address, the 5 last bits to 1. Okay, and we need to convert this, okay, the dotted decimal notation, this binary to the dotted decimal. Okay, so that we will get 167.199.170.95. Okay, so from here we can get the last address or the broadcast address for this network segment. Okay, so I think you need to go through this exercise or this example, and because it might come out in your exam. Okay, so let's continue on classless addressing. Tadi kita dah tahu macam mana nak kira first address and last address. Okay, as I explained before, in the classless address or CIDR, the network part of IP address isn't fixed. Okay, so the slash n number at the end of the IP address tell us how many bits are used to identify the network. So the first address within the group of IP addresses given to network is super important. So this first address ataupun kita panggil juga network address. Okay, think of like the name or ID for the whole network. This address is usually not given to individual computers or devices. So why this network address is important is because it used by routers to send data packets, okay, to the correct destination network. So you can imagine if you have the huge internet that made up of many different network. Okay, so let's say for simplicity, there are M network. Okay, when the data packet travel from source computer to the destination computer on a different network, it will definitely go through routers. Okay, so and kita tengok gambar ni sebelah. Okay, so when your data packet travel from source computer to a destination computer on a different network, so dia akan lalu router. Okay, each one is connected to one M network. When a data packet arrives at this router, the router need to make a key decision. Okay, so which network should this packet be sent? So it's get closer where it needs to go. So which port? So kita tengok kena ada dia tahu which network and which port on itself should be routed to use send this packet. There is where the network address comes into play. Okay, let's see I think the example of the network address here. So this is how the routing process that we just talked about. At the top, we can see the simple view of the internet show the network 1, 2, and until network M. And this represent different network connected to the router. Number 1, 2, and M is the connection shows the interfaces or port on the router. So the interface 1 is connected to the network 1, interface 2 to network 2, and so on. So an incoming destination address, okay, goes into the box level find network address here. Okay, this box show the router's action of taking out the numbers address from the complete destination IP address using the dash n information. Okay, so from this result, the result from this find network address process is then used to look up the information in this forwarding table. Okay, so as you can see here, there are two columns. First is the network address, and you can see the example like b1.c1.d1.e1. So sampailah BM, CM, DM, and CM. So this is just a simple way to represent the different network address. For the interface, it is the router port. Okay, so to send the traffic to the matching network address. Okay, and the arrow from the forwarding table to the interface number show that the lookup process give this specific port that the packet should be sent out from. Okay, so basically the picture or this image shows how router use the destination IP to figure out the destination network address and then check its forwarding table to find the right where is the port to send the packet towards the network. So, let's see the example of what the block allocation restriction. Okay, so for CIDR to work effectively and what efficiently, there are two main restrictions that need to be applied when allocating a block of addresses. The first one is the address must be always the powered of two. Okay, and when an organization like ISP requests a certain number of IP, we call it as N. Okay, the N must be a power of 2. Okay, why? Let's look at the relationship between the number of addresses and the prefix lengths. Okay, we know that in IPv4 the number of address is 32. Okay, so we know that the number of hosts bit in IPv4 is 32 minus n, right? Where n is the prefix length. So the total number of address in a block is then raised to the power of the number of host bits. So n is equal to 2 to the power of 32 minus log 2n. Okay, so sorry, n is equal to 2 to the power of 32 minus n. So we rearrange this equation to solve the n. So n is equal to 32 minus log 2n, which is 1024. And it is equal to 22. And what else? So that is the restriction number 1. The restriction number 2 is the first address need to be divisible by the number of address in a block. So the second important restriction is that the first address of the allocated block must be divisible by total number of address in that block. Okay. So when we convert this binary network to to its decimal equivalent, the host bits being all zeros and contributes nothing to decimal value in terms of powers of 2 corresponding to those bit position. The decimal value of this address is essentially determined by the decimal value of the prefix multiplied by 2 to the power of 32 minus n. Okay, So we can say that the first address is equal to the prefix in decimal times by 2 the power of 32 minus n, and is equal to prefix in decimal times by n. Okay. Okay. Then let's see this example lah. Okay. So let's say the organization get a block of address starting from 14.24.74.0/24, and they need to divide into three smaller network. Okay. So one about 10 address and one about 60 addresses, and the other one about 122 addresses. So uh the subnet number one, sub network number one needs around 122 address. Okay. 120 is not the power of 2. So the next power of 2 bigger than 120 is 128. So we'll give this subnetwork 128 address. Okay. And then we can find the prefix lengths. Okay, of this subnetwork. So N1 is equal to 32 minus log 2 128. Sebab 120 ni tak ada dalam the power of 2. So yang terdekat adalah 128. So log 2 128 is equal to 7. So 32 minus 7 is equal to 25. So the prefix is /25. And so if the question asks you about the first address of this subnetwork, it will be starting the address of the whole block, which is 14.24.74.0/25. Okay, and the last the last address in this subnet will be 14.24.74.127/25. /25 ni tak berubah Okay. So what else? So the subnetwork number 2, which is we need 64 addresses. Okay. And we know that 60 is not power of 2. Next, the power of 2 bigger than 60 is 64. So we'll give this subnetwork 64 addresses. Okay. And the prefix length is N2 is equal to 32 minus log 2 64, and log 2 64 is equal to 6. So 32 minus 6 is equal to 26. And then we can get the prefix is /26. So the first address, okay, the first address is equal to 142474.128. And notice that 128 is divisible by 64. Okay. And the last address of this subnetwork will be 14.24.74.191/26. So you can see the previous slide of how can we find the last address. Okay. And this is the subnetwork 3, which is require 10 addresses. And then we know that 10 is not the power of 2. So the net bigger than 10 is 16. So this is log 2, 16 is equal to 4. 32 minus 4 is equal to 28. And then you can find what is the first address and the last address. Okay. And so how many unused address? Okay, because we had to round up the numbers for each subnetwork to the nearest of 2, we will have some unused address. So for example, for the first subnetwork, we allocate 1 to 8, but we needed 1 to 0. So the unused address for subnetwork 1 is 8. For the second subnetwork is 4, and for the third subnetwork we have 6. So the total of unused unused address is 8 plus 4 plus 6. We have 18 unused addresses. Okay. So about the range of these unused addresses would be from the end of the last used address in the third subnetwork up to the end of the original block. Okay. You can tengok balik lah. The original block is 124 14247 dot 0/25. Okay. Okay, and then the last subnetting is 14.24.7.204. Okay, so the unused address are in the range of 14.24.74.2082 142474255. Okay. So I think by remembering these rules, when you are dividing a network into smaller piece, it will help keep everything organized and make sure our network device can understand and structure. Right. Next is the address aggregation. I would like you to think back to our earlier discussion about routers acting like post office. Okay, so they need to know where to send the mail or the data packets to get them to the right city. The city here is the network. Okay, now imagine if every single house, okay, in the city had its own separate instruction. Okay, at every post office along the way. Okay, it would be a huge and complicated system. So address aggregation is like a grouping. Okay, a grouping houses in the same area under one general instruction. For example, send this send this packet to house number 1, street A. Send this to house number 2, street A, and so on. So we can just send all mail for street A to this local post office. So this makes things much simpler for the main office. And in the world of IP addresses, uh, address aggregation would work similarly. Okay. For example, ICPS get a big block. For example, a global authority that call ICANN. ICANN is Internet Corporation for Assigned Names and Numbers. Okay. It gives large block of IP addresses to the internet service providers, to the ISP. Okay. So here ISP can act as the main postal services for different regions. Okay. And each ISP then will take its big block and divide into smaller blocks, which is if you refer to the post office, it refers to the our streets, and give this smaller block to their customers. Okay. And I think the good or the pros about address aggregation is that if an ISP give out several smaller block of address that are close to each other in the IP address range, they can often combine this smaller block, okay, and advertise them to the rest of the internet as one single larger block. Okay. And why the address aggregation is very useful, because of the simpler routing table. Okay, routers on the internet don't need to keep track of every single small network. They can just have one entry for the larger and for the aggregated block. Okay, and this will make the routing tables much smaller and easier for router to manage, lead to faster and more efficient routing. Okay, and we know that with fewer entries to check, routers can make decisions about where to send traffic more quickly. Okay, so this is the example on how address aggregation works. Okay, imagine that we have an ISP. It's given the large block of addresses. Okay, for example, block 1 is 1607014.0/26. Okay, 2 160.07.14.63/26. Okay, it's from 0 to 63. Okay, and for block 2, 64 to 127, and block 3, 128 until 191, and block 4 is 192 to 255. Okay, so we can see that these are all these blocks are consecutive. Okay, and because they are next to each other, and the ISP, okay, this is ISP, can then combine this four block, okay, into one larger block. Okay, this is from 0 to 255. Okay, so this is all packet with destination address from 0 to dot 255 are now sent to the ISP. Okay, so now instead of advertising four separate routers to the rest of internet for each of the smaller block, the ISP only needs to advertise one route for the larger block. Okay, and when the packet from the internet is destined for any addresses between 0 to 255, the internet routers only need to know to send it to this ISP based on the 160.7014.0/24 block. Okay. So once the packet arrive at the ISP, it is the ISP job to forward to the correct smaller organization within its work. Okay. So what can we say that the address aggregation is the the key component for CIDR, as it helps to keep the internet's routing system scalable and efficient. Okay. This one is the the 5 special addresses that are used for special purposes. Okay. Okay, the first one is this host address. Okay, and it's used by a host when it needs to send out an IP datagram, but doesn't know yet its own IP address, like during the initial startup process. Okay, so it's used as a source address in this very limited situation. The second one is the limited broadcast the limited broadcast address. Okay. So this is used when the host or router needs to send message to all device in the network. Okay. And so it use the address as the out as a destination. How about the routers? Routers, however, are designed not to forward the packets with this address. It's like shouting within your own room. Okay, and we have the loop back address. Okay, with the block of 127.0.0.0/8. So any IP address that start with 127 is a loopback address. For example, if you send a packet to a loopback address, it's never leave your own computer. It's used for testing the network software on machine without need a physical network connection. Okay. The number four is the private addresses. Okay, so these are blocks of IP address that are reserved for use within private network, like your your home network, or a company's internal network. Okay, so for this private address, it is not routable on the public internet. Okay, if traffic with a private destination tries to go out to the internet, it will be stopped by routers. Okay, so so there are four main range of private IP address. We have 10.0.0.0/8, okay, which is ranging from uh, 10.0.0.0 to 10.255.255.255. Okay. Next, we have the 172. Okay. Dot 16.0.6.12. Okay, so what is this? Okay, yang sebelah ni binary ni. Okay, so first we need to convert the first two octal ataupun octets ni into a binary. Okay, so 172 minus 128 is equal to 44. So 64 will goes into 44 zero times. Okay, and then 32 will goes into 44 once, and 16 will goes into 12 zero times. Okay, so this is 172 in binary, 10101100. And then we have 16 in binary. You boleh kira lah macam mana dapatkan 16. In binary, I think it will give you 00010000, and then the rest is zeros. Okay, so this is how you you change from what the decimal to binary. Okay, and for the /12, it's mean that any IP address start with a binary pattern 101100000001, which is the 12 first the first 12 bits. Okay, so this is belongs to the private address range. Okay, and for the multicast address, okay, 224.0.0.0/4. So it is reserved for sending the same data to a group of interested devices. Okay. Right. Now let's talk about how your device um, automatically get their network address. Let's so we call something like DHCP, which is Dynamic Host Configuration Protocol. Okay, so think of like a hotel that give you a room number when you check in. So you don't have to figure it out and set it up yourself. Okay, so DHCP is like the system that automatically assign a network addresses within the organization. It's like the helpful program that working behind the scenes that makes sure your device can communicate on the network. So because it makes connecting a network easy, it's often called as a plug and play protocol. Okay, so the network managers can use the DHCP to give devices either a permanent IP address for things that don't move. For example, you have laptops, okay, and you also can have the um, temporary address, okay. So for example, this one permanent is like your PC lah kat rumah yang tak bergerak. So for the temporary one, you have your laptops, okay. So so why we need the DHCP? Okay, well, it's just like every house need an address to receive a packet of mail. Every device that connect to a network also needs the IP address to communicate with other devices. Now, for some devices like routers and servers, okay, which stay in the same place and always need the same address, we usually set up the static IP address. Okay. But for your computers, laptops, and phones that might move around and only connect sometimes, okay, we it is much easier to use the DHCP. Okay, it's meaning that the DHCP will allow the device to grab any available IP address from set range that a network administrator has set up within the network. Okay, so yeah, let's talk about who usually takes on the role of the helpful DHCP server that hands out IP address automatically. Okay, normally or generally, network administrator in a larger organization prefer to use a dedicated network server to offer DHCP services. Okay, so there are a couple of good reasons, okay, behind this, which is one is scalable, meaning that it's easy to handle a large number of devices requesting the IP address, which is very common in a bigger network. And secondly, it's relatively easy to manage, okay, meaning that the DHCP setting and address assignment from central server, you only have one place to configure everything. Okay. Sorry. Okay. But for the small branch or in the Soho, a small office, home office location, a Cisco router can be configured to provide the DHCP services. Okay. Um, so this is more convenient solution because it can eliminate the needs of separate or potentially expensive server. Okay, and the router, which is already a piece of equipment for connecting the small network to outside world, can also take a task of managing the IP address. Okay. So while uh, this is a dedicated server is often uh, preferred for larger network, a router can be a cost-effective and practical solution for smaller environment. Okay, now let's look at the different ways how this DHCP server can give out the IP addresses. Okay. Um, so there's first one, the manual allocation, where the network admin decide exactly which IP address decide a device will get. Okay. And the DHCP will just send it. Okay, then we have the automatic allocation, where the DHCP permanently give a device the first free IP address that it asks for. Okay, so it will get the same address every time. But the most common method is the dynamic allocation, where DHCP will assign a device an IP address, okay, for a limited time, like when you check in the hotel, the key card to a hotel room that expired after you check out. Okay, so that is mean the dynamic. Okay. So in the dynamic allocation, it will use the client server system. It's meaning that when your device or your client, the client connects to the network and needs the IP address, it will talk to the DHCP server, and then the server then assign, or more accurately, list. Okay, list maksudnya dipinjamkan uh, an available IP address to your address. Okay, so the list is not forever. It lasts for a set list period. Okay, and before that period's end, your device need to ask the DHCP to extend the list if you want to keep using the same IP address. Okay. If your device disconnect or the list expires and you are not renewed, the IP address goes back into the pool of available addresses and can be used by someone else later. Okay. So this way of temporarily assigning address will help make sure that we don't run out of the IP address. Okay. So now we know that the HCP, okay, give a device an IP address. Okay, but it's not only that. Okay, when device get IP address from the server, it can also receive other important network information. Okay, so it's include the computer addresses, the prefix, the address of default router, and the IP address of the name server. Okay, so basically the DHCP set up all the basic network setting for device automatically, making it ready to communicate on the network and access the internet. Okay, so the process of getting this information involve the conversation between the device needing the address, which is the client, and the server. Okay. So it's like um, the client server process. The first client send a request message. For example, hey, I need an IP address and other network info. And then the HCP server then will respond a respond message containing all the necessary. Okay. And previously we discussed how DHCP make ataupun assign the IP address automatically. And now we will look into how what is 64-byte option field. Okay, so you can think of the extension of a basic DHCP message, and it has dual capability. The first one is to the additional information, and the second one is the specific vendor information. Okay. Okay. Each individual option within the 64 byte field follows a specific structure uh, that comprised by three subfield. The first one is 1 byte tag field. Okay, this act as unique identifier for the specific option being included. Okay, it will tell the DHCP server or client what kind of information the subsequent bytes represent. Okay, next we have the 1 byte length field. Okay, and it's indicate the number of bytes in the actual data that follows in the value field. Okay, and finally we have the variable length value field. Okay, this is where the actual configuration data or vendor specific information is stored. So, let's see the example. If the tag field is 53, okay, the value field defines one of the 8 message type. Okay. In this particular example, the value field is used to define one of the 8 fundamental DHCP message type. Okay. So this is how DHCP client and server communicate the different stages of the IP address. Okay. So we have the number listing start from the DH CP discover. Okay, this is like a initial broadcast client cell to locate available DHCP servers on the network. Next, we have DHCP offer, which respond to the message, then propose the IP address and other configuration parameters. Okay. Oh, yes. And then number 3, we have DHCP request. The client will use this message to either accept a service offer or to request a renewal of IP address yang dipinjam tadi lah. Okay, and then we have DHCP decline. When the client detect that the offered IP address is already in use, okay, it inform the server with this message. Okay. Number 5, we have the DHCP pack. The server will send this acknowledgement to confirm the successful of the IP address and other configuration to the client. DHCP NAC is if the server cannot fulfill the client request, it will send this negative acknowledgement. Then number 7, DHCP release is when a client no longer needs its assigned IP address. So it will send this message to the server to return it to the available pool. Okay. And lastly, we have the DHCP inform. A client might use this message to request additional configuration parameters without need to obtain a new address. Okay. So so for the tag, the first byte is the tag. Okay. in this specific example, the tag is 53, which refers to this number. Okay, this immediately signal that this option field is specify the DHCP message type. Okay, the second byte is the length. Here is one indicates that the subsequent value field is a single byte in length, and the final byte of is the value. Okay, since the tag is 53, the single byte will contain a numerical value from 1 to 8. Okay, and therefore, when the HCP pocket contains an option with a tag of 53, the value within that option acts a crucial indicator for packet purpose within the DHCP communication. Okay, and this is the fundamental mechanism on how the device dynamically obtain and manage their network configuration. Okay. So this is basically the what the how the process, okay, the HCP process. Okay, you can think of the client, which is the network. Sorry, the laptop want to join the network. Okay, okay. So imagine you have the new laptop connect to our network. Okay, so it doesn't know the address yet. So the first thing that it will do is to shout out hello. For example, uh, is there any available address? Okay, I need the address. So the DHCP discover. Okay, so we'll conduct this request lah. Okay. So you can see here, okay, source port 68 and destination port 67. Okay, because it doesn't have one yet, it will shout out to everyone. Okay, so for example, the destination address is this. Okay, using the port number 68. Okay, and then now we are in the um, sorry the DHCP server, uh, we can see this is the IP address of DHCP server 181.1.4.1.6 and 170. It hears this shout, okay, and then it will respond using the DHCP offer, okay, and then it's like hey apa laptop baru, uh, I want to offer you the address of 181.1.4.1.6 and 182. Okay, so and it is only the least time give to you is 3,600 seconds, about 1 hour. Okay, and we can see the second box here. Okay, the server send this offer back to the client using its own port 67. Okay, and the client will receive this offer and might also receive the offer from other DHCP servers too. Okay, and it can choose one offer and say yes, traffic controller, I will take this 181.1.4.1.6 182, or yeah, I can I take this at this server. Okay, and then this acceptance is the DHCP request message. Okay, so Finally, the chosen DHCP server will respond back with the DHCP pack with DHCP act, which is the acknowledgement. Okay, this is like the server saying, great. Okay, server cakap, okay, baguslah, you dah dapatlah IP ni 181.1.4.1.6 and 182 for the next hour. Okay, so here's the network information you need. Okay, so apa yang dia bagi the IP address, the lease time, and the other details. Okay. So in a simple term, first ada 4 step discover ialah the client ask for the address, and then we have offer. The server will propose the address, and then we have the request where the client accept the offer, and then we have the acknowledge where the server confirm the assignment.